All right, so there was a quick video just demonstrating what we might have done in a distant past when we didn't have allergies in school and when we were not doing virtual. But if we can imagine sampling Reese's Pieces, sample size of 40, and we get, what was it, 18 orange, that would be 45%. We may not have found exactly the percentage. Maybe it's 50%, maybe it's 48%. We got 45% one time, but we know we can build what's called a confidence interval based on what we learned last time. We can build a confidence interval and go out and be pretty sure that somewhere in between the two numbers we get, we have found the true percent orange in that bag in some population. So let me go through, I'm going to go through kind of A to Z from start to finish. You saw the actual process if you were sampling for real. Now, what I'd like to do is show you the calculations so that you also have a great example, step by step, top to bottom, of exactly what you'll have to do, calculating by hand, so to speak, from scratch or whatever. So let me bring up Notability. Again, we found out that our sample proportion was 18 out of 40 or 45% orange. And now we want to go out 2 standard deviations, which is kind of just a common distance, go out 2 standard deviations. And we know that if we go out that far, that we would be 95% confident. So let me kind of walk through this just a little bit. And I got 45% this one time, and I want to build a confidence interval. But let's just go back and review just a little bit of the theory behind the scenes. So we know from chapter 7 that sample proportions, if you do everything correctly, pile up roughly normally with a certain standard deviation, and the true proportion will be the mean of this sampling distribution. And I got this one time, I got 45%. But here's the problem. I don't know which p hat I got. Did I get a p hat in the middle? Did I get a p hat on the left side, right side? I don't know, because in real life, I do not know the true percentage orange before I start the problem. So it could have been this one. Maybe I got this p hat. And if I go out 2 standard deviations, well then, I certainly will capture or overlap or contain the true proportion of orange if that happens to be the p hat that I got this one time. If the p hat was over here, it's a little further out maybe, and it's on the right side. But if I go out 2 standard deviations on both sides, again, that interval will overlap or capture or contain the true p, whatever it is. However, if my p hat would happen to be out here and I go out 2 standard deviations, you'll notice that endpoint on the right does not quite capture, does not quite overlap the true proportion. And there's a few of them, there's a few out of these that are going to be that way. If you end up just unlucky and you get a p hat that's more than 2 standard deviations away, well, then when you build an interval, it's not going to capture it. But the good news is most of those p hats, when you go out 2 standard deviations, will in fact capture or contain the true proportion that we're looking for. That's why we can be 95% confident, because of that thing. So here's kind of the thinking, that since 95% of the p hats are within 2 standard deviations of p, which is the true value, then we believe that 95% of the 95% confidence intervals that we would build will contain the true population parameter p, whatever that happens to be. So that's where we get our confidence. That's the theory. That's the bedrock underneath all of the stuff that we're going to do really from now to the end of the course. So now let me go back and actually kind of show the, the kind of the nuts and bolts, I guess, as you would say, the, the things that you would have to do as a student, top to bottom. If you got a 45% p hat, then we are ready to build a confidence interval. So basically, we're going to start with our 45%, and we're going to go above and below a certain number of standard deviations. But now we need to take just a little side journey over here. Let's just double check. We know that 2 standard deviations is about 95%, accounts for about 95% of whatever's under a normal model. But let's go back and just double check that. So we know that if we wanted to have 95% in the middle, back to our normal model, if we want 95% in the middle, we believe that it's about 2 standard deviations based on something we've learned a long time ago. But let's just kind of forget about that. Let's just pretend we don't know whether it's really 2 standard deviations or not. And we would like to find that value. So let me just put an X out here. And, the rule of thumb is that it's 2. That's 2 standard deviations. But let's just double check the work. We want this middle area to be 95%. So how do we find the X? Well, this is a normal, a standard, I should say, a standard normal model. So the mean would be 0, standard deviation would be 1. And all we have to do to find this number is do inverse norm of the percent left. However, the percent left of X is not 95%. It's actually 95% plus this little tail, which being perfectly symmetric, this tail would be 2.5%. There'd be 2.5% on both sides. So if you do inverse norm, you actually have to do inverse norm of 0.975, because to the left of X is actually 97.5% of the area under a normal curve. And if you do that, here's maybe a little surprise. If you do that, it's 1.9599, or if we rounded it off, we would just call it 1.96. So here's the first big revelation. From now on, we're not going to use 2 standard deviations, because actually that's off a little bit. It's a little too big. The truth is, if you want to be 95% confident, you really only need to go out 1.96 standard deviations. So we're only going to go out 1.96 standard deviations, because that's just a little bit more accurate. So now we're switching from a rule of thumb to precision. We're going to be just a little more precise. And then the standard deviation formula, as you know, is the square root of p times 1 minus p over n. But time out. We don't know p, do we? Because we're now in the kind of real life scenario. The real life scenario is you don't know the true proportion of the thing that you're trying to find. So how can we possibly use the formula with p and 1 minus p when we don't know p? Well, in stats, you'll find out that sometimes if you don't have what you want, you just use the next best thing. The next best thing that we do have would be an estimate for p. We don't know what p is, but we know what p hat is. And if we sampled randomly, it ought to be pretty close. So we're going to use 0.45 and 1 minus 0.45, which of course is 0.55. I'll just do that in my head. And then my sample size for this little activity was 40. So now, because we really changed the formula, we really should not call that the standard deviation anymore. So we're going to use a slightly different terminology for that now. That's going to be called, instead of the standard deviation, that's going to be called the standard error. The standard error of our statistic, which is p hat. So it's just a slight nomenclature difference. So instead of standard deviation, it's called standard error. And remember, the word error really doesn't mean mistake. It means more like variation. So instead of calling it the standard deviation, we're going to call it the standard error, which is really just the standard variation, just to remind us that we're kind of using an approximation of the real thing by using p hat instead of p. So now if we do our calculation and add or subtract this bunch of stuff there, which that ends up being 0.154175, I believe. So if you add and subtract that number from 0.45 and round to 3 digits, you get about 29.6% to 60.4%. That is our confidence interval. We went out almost 2 standard errors on both sides, and we got that interval, and we would be 95% confident. So if we were interpreting this, we would say, I am 95% confident that the true percent orange Reese's Pieces in my bag is between 0.296 and 0.604. And remember, it's this context because my bag was actually the population, that little bag I had. So that bag was the population. I took 40 out of it. Technically, I didn't meet the 10% condition, but it was close enough to kind of let that slide. So that would be the interpretation. I'm 95% confident that the true percent orange is somewhere between basically about 30% to about 60%, somewhere in there. All right. Now, just a couple other little things. I already told you about the standard error. That's just a little different nomenclature that we have to kind of adjust to. And then one other thing that I should point out is this entire number here, that includes two pieces. It's the 1.96 number and then the standard error formula. That is the margin of error. That's what we call the margin of error. And again, it doesn't really mean margin of mistake. It just means margin of variation. This is how much variation. There's about 15% on each side of 45%. That is just due to random sampling variability. It's common, it's known, it's real life. And so we think it's around 45% plus or minus 15%. That 15% is just natural sampling variability that occurs even when you do everything correctly. So we end up thinking that the true percent orange is somewhere around 30% to 60%. So that number, 15% roughly, or that calculation there is considered the margin of error. And then one last thing that I will point out is the 1.96 number. This number, which was almost 2, is called the critical value. It's called the critical value. The critical value is just how many standard deviations you go above and below. Now for 95%, it's roughly 2, technically 1.96. If we wanted to be more confident, we'd go out further. We'd maybe make it 99% confidence. And so then we'd have to go out a little further, like maybe 2.576. If we don't need to be quite as confident, because maybe it's not life or death or something like that, maybe we just want 90% confident, then maybe we'd only go out about 1.645 standard deviations. Now, how am I getting those numbers? I'm throwing these numbers around like they're exactly right. Well, they kind of are. Fortunately, on your formula sheet, there is a table called Table B. So if you flip through, I don't know, it's like page 7, I think, in your packet of formulas. If you find Table B, which is a t-distribution table, we will learn about that down the road a little bit. But at the very bottom of the t-distribution table, you will find something very helpful. The last 2 rows are confidence levels and critical values. And notice for a 95% confidence level, right up above that is our magic critical value, 1.96, and it's the accurate one. So for 99%, that's where I got that 2.576. If you go out 2.576 standard deviations on both sides of the mean, that'll be about 99%. And then 90 is another common one we use. You only need to go out 1.645 standard deviations and you'll be 90% confident. So if you need to look up any of these, of course, you can calculate them with inverse norm too, but this is kind of a quick way to find some of the common ones that are used in confidence intervals. So those are some other critical values that you can find. And after you do a bunch of these, you'll probably just memorize those 3 numbers like I have. That's just part of the deal. And then when you, if we kind of just can wrap up here by doing a formula, let me show you the general formula for confidence intervals of p hat. So here's kind of the general formula that you're going to use every time. So let's see, I don't know if I can put this on the same screen or not. Maybe I can. I'm basically going to write down these 3 numbers, the 45 and the 1.96, and then this formula here. Those are the 3 components of a confidence interval for p hat. So the confidence interval formula, and this is for when you have a sample proportion. We start out with our statistic and we add or subtract the critical value, which is going to be some z-score, some z-value, times the standard, turns out to be standard error formula, which is p hat times 1 minus p hat over n. That's the confidence interval formula for any confidence interval that you make trying to estimate P from a p-hat. Now, in our particular case, you might remember that our numbers were 0.45. Our Z-star number was 1.96. That's how many standard deviations we went out. And then in our formula, we used 45% and 55%, and our sample size was 40. And that's how we got our final answer of 0.296 and 0.604. So the general formula is the one with all the fancy variables. And then we just have to substitute in all the numbers that we need. So that is generally the nuts and bolts of confidence intervals for sample proportions, estimating the true proportion. And so from the formula, even if you're a decent algebra student, when they ask you questions like, well, what if you want to increase the margin of error? Well, you can look at the formula and think, well, if I want to increase the margin of error, I guess my choices would be to increase that number, the Z-star, like go out further, or I could decrease the n, because decreasing a denominator will increase the entire fraction. What if you want to, what happens if you increase your sample size? If you decide to take a sample that's twice as big as it was before, well, if you increase your sample size, that's increasing your denominator. And when you increase your denominator, you'll decrease the standard error, which decreases the margin of error. So this formula also can inform you when they ask you questions about, well, what if you want to do this? What if you want to do this? You can kind of see the interplay between the critical value, the sample size, and even the p-hat. Although the p-hat probably isn't something you can physically change. You can usually decide to change your sample size, and you can decide to change your critical value and your confidence. So those are the things that normally get changed. So there you are. There's nuts and bolts, top to bottom. And hopefully soon we'll meet in class and get a chance to answer any questions. Be sure to do your practice problems. Those are so critically important, to do as many different kinds of problems that you can, experience different confidence levels and different scenarios so that you get a lot of variety in your toolbox. So I will see you soon.